conditional call, so far whatever call and return we have seen, so that were unconditional. So, the call instruction will definitely take the control to the subroutine, and return instruction will definitely take you back from the subroutine. Sometimes we need some conditional call and return instructions like the CC instruction. So, call subroutine if carry flag is set. Similarly, CNC is call subroutine if carry flag is not set. So, like that we can have some conditional calls. Similarly, RC is return from subroutine if carry flag is set, and RNC return from subroutine if carry flag is not set. Then we have got this 0 flag. So, CZ call if 0 flag is set. So, like that we can have. So, all these condition codes that are allowed with these conditional branch instructions. So, they are all allowed with this conditional call instructions also, but they are much less practiced compared to these branch instructions, because that makes the code complex and difficult to follow while reading. So, that is so normally what is done is that we do some jump, some conditional branch checking, and then put the call instruction on top of that. Okay. So, we try to make it as straight line as possible. Okay. So, that way it has to be done. Now, how to write a subroutine, like what should be the what are the general guidelines for writing a subroutine. So, proper subroutine is only entered with a call and exited with an RET instruction. So, that is it has got a single entry point. So, do not use a call statement to jump into different points of the same subroutine. Should has it. Okay. So, what we mean is the guideline is like this. This is assembly language programs. So, since the control is entirely in the hand of the programmer. So, if this is my subroutine, and suppose my subroutine starts at location say 2000, it starts at location 2000. Now, you should issue instructions like call 2000. So, that is fine. So, this subroutine, suppose it spans from 2000 to 3000. Now, it is highly possible that I put a call instruction for location 2500. So, that is possible, because 2500 is somewhere in between. So, this particular call will start from this point onwards. So, processor does not differentiate between whether this is a subroutine or not, but the processor will not differentiate between whether this is a subroutine or not. So, it will always take you from this address onwards. So, 25. So, if you whatever address you mention, so it will take you to that address, and it will go from there. But so it is, but as you can understand that if you have got several such entry points inside the subroutine, then the branching becomes understanding the program becomes difficult. So, this is exactly what is done here, done by the programmers. The programmer has to be careful and has to take into consideration that I should not branch into the location inside a program. So, do not use a call statement to jump into different points of the same subroutine. So, that you should not do, and similarly we should have a single exit point. So, somewhere here in the program I put an statement, in the subroutine I put a statement like jump to say 1500, that takes it outside the subroutine. So, we should not do that, because then we have got some exit point, so which is not really very valid one. So, there should be only one return statement from any subroutine. So, these are the guides from the software engineering angle. So, as far as the processor instruction execution is concerned, so these are not at all any restriction. So, the programmer is absolutely free to do all these things, and assembly language programmers, so they have got the highest level of freedom. So, they can write programs in any style that they feel like. Okay. So, there similarly this if it is for push and pop, we have seen that there are some rules like push and pop should be done in the reverse order and all. So, those rules, if they are followed properly, so that will avoid any confusion that can arise due to this push pop instructions. So, that is there. Next, we will be looking into another very important concept, which is known as interrupt. So, interrupt is a process where an external device can get the attention of the microprocessor. So, in our day to day life also interrupt is very common, like say suppose we are sitting in a room and reading a book, and then all on a sudden the doorbell rings. So, we have to go and see like what attend give attention to why the doorbell has ring, somebody has come or not, etc. Now, the first thing that we should do is that we should keep a note like which page of the book I was reading, so that I can come back and start reading from that point. So, that is the first point. Then even before that, maybe we were reading one line, we were in the middle of a line. So, we first finish off that line and then note down the page number, maybe by means of a bookmark or so. So, we keep a note of the page that we were reading, and then go to attend the door call, and then after doing the whatever, after talking to the person who has arrived, and then maybe we again come back and start reading the book. So, that whole thing is an interrupt process. So, similarly the processor, when it is in its normal execution, what it is doing? So, it is just getting the next instruction from memory and executing it. After that, it is again getting the next instruction and executing it. So, there is no way by which I can tell the processor, see, something emergency has happened. So, you need to look into this part and do the operation. So, so that until and unless the processor is asking for some input output type of operation. So, we are not getting any chance to tell the processor that something extraordinary has occurred and you have to take care of this, you have to do something for this. So, this is the process of interrupt. So, this is interrupt is a process where an external device can get the attention of the microprocessor. The process starts from the I/O device and the process is asynchronous. So, it starts on the I/O device, means the I/O device will tell the microprocessor that there is something emergency that has occurred, and it has to process that operation. And it is asynchronous because when this interrupt will come, so there is no such there is no such fixed timing for that. So, so processor works in a synchronous fashion. So, it works at the with the clocks and or the as some clock frequency and all, but this interrupt can come at any time. Some of these interrupts are maskable interrupts, because you may you can make the processor, you can say that okay, it will wait for some time, and some of them are non-maskable interrupts. So, they cannot be delayed. In terms of our day to day life, so suppose this micro oven whistle goes, that means the say the food is ready. So, we know that even if if you keep the food there for some time, nothing is going to happen. Okay. So, we can it is a maskable interrupt. So, we can do it later, it can be delayed, and somebody making a pressing the doorbell, maybe we need to attend it immediately. So, that has to be done immediately. So, that is non-maskable. Then interrupts can also be classified into vectored interrupt and non-vectored interrupt. So, vectored interrupt means the address of the service routine is hardwired. So, the processor knows the address of the subroutine to be executed when this interrupt occurs, and the non-vectored interrupt. So, address of the subroutines need to be supplied externally. So, what we mean by this vectoring, maybe we can explain further. So, it is like this. See, this is the, if this is suppose this is the program that the processor was executing. So, this is the program P that the processor was executing when the interrupt occurred. So, when the processor was at this particular line, the interrupt has occurred. Okay. So, then interrupt has come. Now, what the processor will do ultimately? So, processor has to process this interrupt, and processing this interrupt means again executing some routine. So, what is done depending upon this type of interrupt, maybe this interrupt is to that the user has pressed a key and that has generated an interrupt, or user has moved the mouse and that has generated an interrupt. So, what the processor is supposed to do is to read the character that has been pressed, or read the current mouse location, coordinate of the current mouse location for some purpose. So, that for those operations, that is reading the key, the content of the key, or reading the mouse position, etc. So, there are routines. So, this may be the keyboard routine, which will be reading the keyboard. This may be the mouse movement detection routine. So, if this interrupt is a keyboard interrupt, so these routines are already loaded into the memory. So, one possibility is that the processor already knows that for the keyboard interrupt, so what is the address from where the program be executed. So, when this keyboard interrupt comes, the processor immediately branches to this address. So, that is one possibility, and the other possibility is that the processor does not know where to go. So, in that case the device that has generated the interrupt should tell the processor that what is the address of the service routine, the corresponding service routine. Maybe for the mouse, it does not, the processor does not know like where to go if the mouse interrupt occurs. In that case, the processor should this address of this mouse routine should be provided by the mouse device itself. So, it should tell the processor, okay, this is the address. So, once the mouse device tells the processor that this is the address, then the processor will go to that particular address. So, this is the difference between the vectored interrupt and non-vectored interrupt. So, in case of vectored interrupt, the processor knows the service routine address where to go, and in case of non-vectored interrupt, so processor does not know the service routine where to go. So, in the second case, the processor has to get the address from the device. So, this is the difference between this vectored and non-vectored interrupt. So, in case of vectored interrupt, the address of service routine is hardware. So, it is fixed by the designers, and in case of non-vectored interrupt, so this needs to be supplied externally by the device. So, in terms of an interrupt, so it can be considered to be an emergency signal, and microprocessor should respond to it as soon as possible. So, as soon as possible it should be responded to. When the microprocessor receives the interrupt signal, it suspends the currently executing program, jumps to the interrupt service routine or it is interrupt service routine. So, this is also known as ISR in short, to respond to the incoming interrupt, and each interrupt will most probably have its own ISR. So, in some cases some of the interrupts may be grouped together to have a common ISR, but in general each interrupt should be is of different group. As a result, it should have a different type. So, it should have a different service routine. So, if we try to look into the spaces, the steps that it should take for responding to an interrupt. So, the steps that are needed for responding to an interrupt, the first thing that the processor does is that, so when interrupt occurs, the first thing that it should do is to complete the current instruction. As you know that every instruction may be spanning over number of clock cycles depending upon the type of instruction. So, it may span over a number of clock cycles. So, it should complete the current instruction. After completing the current instruction, the next thing that it should do is to save the return address, onto stack, and then it will branch to the interrupt service routine. Now, in case of vectored interrupt, the interrupt service routine address is known. So, in that case branch to external the interrupt service routine is easy, or this it is basically a call instruction. So, this program counter values will be saved onto the stack and it will be going to the interrupt service routine. But in case of non-vectored interrupt, so this ISR address is not known. So, in that case it will go into some other, it will be doing something extra to get the interrupt service address, and from where it will execute. After getting that address, it will go to the branch to that ISR. Now, so this is the three things that the processor does before going to the ISR. Now, if we look into how do we respond to an interrupt. So, this may be immediate or delayed depending upon whether the interrupt is maskable or non-maskable, and whether interrupts are being masked or not. Some of the interrupts are maskable interrupt, some of them are non-maskable interrupt. Like in case of processors, so you can say the power failure is a non-maskable interrupt. So, so that if there is a power failure, then that is a very severe thing, because the entire system is going to come down. So, that way that is a non-maskable interrupt. and some other interrupts may be maskable. So, that is the user may think that okay, I should not this program should not be disturbed by all these interrupts. Okay. So, that way you can mask out the interrupts, so that those interrupts will not come, will not disturb the program being executed. So, this interrupt may be maskable, interrupt may be non-maskable. So, if it is a maskable interrupt, then user has a choice to mask out the interrupt. So, if the interrupts are masked, then they will not be responded immediately till the user again unmask the interrupts. So, there are two ways of redirecting the execution to the ISR, depending on whether the interrupt is vectored or non-vectored. So, vectored interrupt means the microprocessor already knows the ISR address, okay, as I already said, and in case of non-vectored interrupt, the device will have to supply the vector to the microprocessor. So, that is the non-vectored interrupt. In case of 8085 processor, the maskable interrupt process in 8085 is controlled by a single flip flop inside the microprocessor, which is known as the interrupt enable flip flop. So, this is controlled by two instructions, enable interrupt and disable interrupt, EI and DI. So, it has got 8085 has a single non-maskable interrupt, and this is this non-maskable interrupt. So, this interrupt cannot be affected by this EI and DI instructions. So, they are always enabled. So, whatever program is being executed, if it finds this interrupt has occurred, non-maskable interrupt has occurred, that will always be serviced by the microprocessor. So, this is the it has got this maskable and non-maskable interrupts by, and this maskable interrupts can be masked by DI instruction, they can be unmasked by EI instruction. So, 8085 has got 5 interrupt inputs. Well, the first one is the INTR. So, INTR is it is a non-vectored interrupt, and in case of 8085, so there is only one non-vectored interrupt, which is INTR, and the INTR is maskable using the EI and DI instruction pair. So, it can give this so if the processor thinks or the user thinks that I should not be disturbed by INTR for executing some part of my code, so it can put a DI instruction at the beginning of that code and then EI at the bottom of the code. So, it is like this. Suppose this is a piece of program that I want to execute, and out of this code, so in this part, so I do not want to get disturbed by the maskable interrupts. So, what you do, you put a DI instruction here and an EI instruction here, so that for during this part of execution only the non-maskable interrupts, so they can interrupt the program. Maskable interrupts, so they will not be able to mask the interrupt the system. So, in case of this INTR, so this is a non-vectored interrupt. So, this the ISR address is not known to the processor directly, and then this is also maskable because it is by means of this EI-DI pair. There are some more instructions, RST 5.5, RST 6.5 and RST 7.5, they are automatically vectored. So, they are vectored means their ISR addresses are known. So, it will be the processor will jump to a particular address, and all these RSTs, they are maskable. Okay. So, all of them are maskable, and they can, the trap is the only non-maskable interrupt in 8085, and trap is also automatically vectored. Okay. So, our trap is basically similar to RST 4.5. So, to summarize, so INTR, RST 5.5, 6.5 and 7.5, they are maskable interrupts, and trap is a non-maskable interrupt, and this INTR, as far as vectored non-vectored classification is concerned, INTR is a non-vectored interrupt, and RST 5.5, 6.5, 7.5 and trap, so they are all vectored interrupts. Now, how this vectoring takes place? Okay. So, for the vectored interrupt, so there is something called the interrupt vector table or IVT. So, any processor that is supporting a vectored interrupt should define some part of memory which is called the interrupt vector table or IVT, and the specific locations in the IVT are dedicated to different vectored interrupts, and what the processor is expecting is that in that location. So, you should put the interrupt service routine should start from that location. So, this an interrupt vector is a pointer to where the ISR is stored in the memory. All interrupts, vectored or otherwise, are mapped onto a memory area called interrupt vector table. This interrupt vector table usually located in the memory range 00, that is 0000 to FFF, that is first 256 bytes. Okay. And the purpose of this interrupt vector table is to hold the vectors that redirect the microprocessor to the right place when an interrupt arrives. And IVT is divided into several blocks. Each block is used by one of the interrupts to hold the vector, hold its vector. So, if you have got a n number of interrupts, then this range of this 256 bytes. So, it is divided into n such blocks, and each block will have the it will hold the vector for the interrupt, one vector for the interrupt. So, in case of 8085 processor, so for the non-vectored interrupt process, that when it is not non-vectored, so how does it operate? So, this is the vector process should be enabled using the EI instruction. The EI instruction must be executed sometime earlier by the processor, okay, for the interrupts to be enabled. And the 8085 checks an interrupt during the execution of every instruction. So, what happens is that so this 8085 instruction, so that is so it is taking a number of cycles, a number of T states. So, suppose this is so these are the different T states that the processor is taking for executing. So, if this is the last T state, so in this T state, so it will check whether any interrupt has occurred or not, and then if the interrupt has occurred, then after finishing the current instruction, so it will go to that interrupt service routine. Okay. So, this is the point. So, the last but one clock cycle, of the total instruction execution. Okay. So, in every instruction execution, the last but one clock cycle, it will check the interrupts, and if it finds that some interrupt has occurred and it needs to be serviced, then it will be branching to that ISR routine after finishing the current instruction. So, if there is an interrupt, the microprocessor will complete the executing the instruction and start a restart sequence. So, restart sequence is the interrupt vector, so somehow the interrupt service process. Okay. One thing you must note that it always completes the current instruction. So, it is not that it leaves the first the original instruction halfway done. So, it is not like that, it finishes the current instruction and then it attempts to go to the interrupt service process. It starts a restart sequence of operations by which it will be doing the interrupt servicing. What is this restart sequence? It first resets the interrupt flag, that interrupt enable flag IE. So, this is disabled. So, this becomes DI. So, that is so this, and then it will start one cycle which is known as an interrupt acknowledge cycle. So, in case of 8085, if you remember that there are two pins, one is the one pin was a INTR, which is an interrupt line, and then there was another pin going out which is INTA bar, interrupt acknowledge bar. So, this actually tells that this is actually used to tell the device that the interrupt has been received by the 8085 processor. So, if this is your 8085 processor and this is the device, now this device has given an interrupt to the 8085. Now, the device must be told that okay, that its interrupt has been accepted. Okay, then the processor is going to do the associated operation. So, somehow this has to be told. Okay, so, that is the role of this INTR and INTA bar lines. And as you know that since INTR the address is the ISR address is not known, then the device should somehow supply this interrupt address, the interrupt service address to the 8085 processor. So, we will see how it can be done. Now, In case of so upon receiving this INTA signal, the interrupting device is expected to return the opcode of one of the RST instructions, one of the 8 RST instructions. So, in general these RST instructions are like this. So, this so this RST n, so this n can be a 3-bit value. This n can be a 3-bit value, and what the processor does is that it multiplies this what the processor does is that it is like this. So, this is the 8085 processor and this is the device. Now, it has given the interrupt and it has put the interrupt acknowledge line. Then the processor, the 8085 expects that the device will put one 8-bit code here. So, this is the data bus line, this is the data bus line of the processor, and it expects that one 8-bit value will be coming here, which will correspond to one of these RST-n instructions. Okay. So, upon getting that, it may be that device has got some special register here, one 8-bit register here, which holds the ISR address, and this interrupt acknowledge signal, when it reaches this register, so it puts the content of those content of the register onto the data bus. In this way, the device may have some device address register, and that address register is nothing but the address of the ISR that it is executing, that should be executed to get the interrupt serviced. So, this data bus on the data bus, so it will expect that one of the RST instruction code will be put here, and this 8085 processor, so it will execute the RST instruction then. So, so that this RST instruction, so that actually transfers the control to some location, this whatever be the value of this n. So, depending upon that, it will jump to a predefined, pre-specified location, and from that point onward the processor will start executing. So, it is expected that this interrupt service routine for this device is located from that particular address. So, this way this vectored interrupt can be non-vectored interrupt. So, this non-vectored interrupt, so this so it will be doing it sorry. So, this will be So, this receiving the INTA signal, this interrupting device will put the opcode of one of the 8 RST instructions, and upon getting this opcode, this RST instruction, so it will save the address of the next instruction in the stack and jump to the appropriate entry in the interrupt vector table. And this interrupt vector table entry, must redirect the microprocessor to the actual service routine, because the space may be small. So, in the interrupt vector table, so it may hold a branch instruction to a later part in the memory, where it actually loads the entire service routine. Then the service routine will be executed, and at the end of the service routine there should be one return instruction that will return the execution to the original program at where the interrupt was received.